Welcome to the video on skewness. Let me get the title up here for us. Skewness. Let's just start with a definition here of skewness. Skewness is just the degree of asymmetry of the normal curve. And you remember kind of a standard notation for the normal curve here is capital N with a mean of 0 and a standard deviation of 1. Okay, so what I want to do is just show you the mathematical calculation of skewness, and then in another video we'll show the kind of basic graphical interpretation of what skewness might look like, but I want to show you the calculation first. So I've preloaded a data set here. And if you remember, this is the same data set that we've been working with in our other videos looking at years of employment. 7 years of employment here, 8, 8, 7, so on and so forth. And so x sub I means every ith raw score. So when I equals 1, it's the raw score 7. When I equals 2, it's the raw score 8, so on and so forth. And so if you were to sum all of these x sub I scores, you will get a sum down here of 60. And then if you remember the formula for mean, x bar equals the sum of I equals 1 through n of the x sub I scores divided by n. So just take 60 and divide by n here. So 60 divided by 10 equals a mean of 6. So again, just doing this in the long, kind of non-algebraic way here, then what we want to do in here is add a 6 next to each one of these numbers. Okay, just kind of, again, doing this very long-handed here so we can kind of show what's happening from the arithmetic standpoint. So this next column, so first column was our index of summation value. The second column here is the actual raw score equivalent to that index of summation value. Third column is our mean. The fourth column here says x sub I minus x bar. So that's taking, if we just kind of call this, I'll put it in blue here, call this column 2 and column 3 and column 1, then what this is saying is take column 2 here minus column 3. And so what does that mean for us? Well, 7 minus 6 is 1, and 8 minus 6 is 2. Another 8 minus 6 is 2. 7 minus 6 is 1. 3 minus 6 is negative 3. 1 minus 6 is negative 5. 6 minus 6 is 0. 9 minus 6 is 3. Again, we have another negative 3 here. And then 8 minus 6 is 2. And if you were to sum all these up, you would get 0. So we can't do anything with these deviations. At this point in time, this fourth column here, the xi minus x bar, is how far every raw score is from the mean. But when you do that, you'll get a sum to 0. So what we have to do is square these values so they will no longer sum to 0. So in this fifth column, you're seeing x sub I minus x bar squared. And so then what we need to do is take each value in column 4 and square it. So 1 squared is 1, 2 squared is 4, this is a 4, this is a 1, this is now going to be positive 9, this will now be positive 25, 0 squared is 0, this will be 9, 9 again, and 4. And so if you sum this column now, instead of equaling 0, it will now equal 66. Okay, and if you remember going back to our video on measures of variability and looking at variance and standard deviation. So if you remember the formula for variance variance was s squared, and it was the sum of the x sub I minus x bar squared divided by n minus 1, which was our degrees of freedom, which gave us 66 divided by 9, which gave us sorry about that, it gave us 7.33 if I recall. Kind of put these in boxes down here. And then if you recall the formula for standard deviation, because we're going to need this in just a minute, the standard deviation was the square root of the variance. So in this particular case, that would give us 2.71. Okay. So now with all of this in place, we can now get back to the issue of skewness. So why did we have to do this? Because if you remember the formula for a z-score, well, let me put the formula down here for actual skewness. So skewness formula, put this right here. It is denoted by the Greek letter gamma, which kind of looks like a y sub 1. So it's called gamma 1 equals the sum from I equals 1 through n of the zi cubed scores divided by n minus 1. Okay, so what do we need? We know everything in here except for we know what n minus 1 is, and we know how to sum, and we know how to create a z-score, but now we need to cube that z-score. So if you remember, the formula for the z-score was xi minus x bar divided by the standard deviation. So this standard deviation piece right here is why we had to come over here and calculate this standard deviation piece here. So everything to this point has been a review of the other videos that we've had up into this point. And so what we need to do now is calculate z-scores. Well, the numerator we've already calculated here. This piece right here for z-score is a deviation score, x minus x bar, and that is this piece right here, right? So we already have that column. And so all we have to do now is create a column that says z-score, and then we need to, and we can just kind of show the math on the first one, but then you would take the deviation score, put it in red here, this 1 would be in the numerator, and then this 2.71 down here would be our denominator, because it's the standard deviation piece. So let's just show that. So it'd be 1 divided by 2.71 equals 0.37. Okay, so if we were to go in here and do this same math for all these, we'll just show the next one, 2 divided by 2.71, and give you 0.74. So if you just keep doing the math all the way down, the next one's 0.74, next one's 0.37, next one's negative 1.11, next one's negative 1.85, z-score of 0 is still 0, then you have 1.1, negative 1.1, and 0.74. Okay, so now all we have to do to get the skewness value is we have to take this z and we have to cube it. So if you go back down here to the skewness formula, we have to deal with this piece right here, which is taking z multiplied by z multiplied by z. And so if you do this, so we're now talking about a z cubed column, it would be taking this 0.37 multiplied by 0.37 multiplied by 0.37, which would give you 0.05 equals 0.05. We want to do the same thing for all of these. So if you go, the next one would be 0.41, 0.41. This one's 0.05, negative 1.33, negative 6.33, 0, cubing 0 is still 0, 1.33, negative 1.33, and 0.41. And so now we have everything we need to be able to complete the actual calculation, because the only thing we have to do now is sum. That's what this is saying. Sum from I1 through n, so that means 1 through 10 in this case, of all these cubed z-scores. So essentially down here what we want to get is a sum value and our sum value here is going to be negative 6 point, actually let me just double check the math on this real quick while we're still here. I'm just going to pull the calculator, see 0.05 plus 0.41. Just stay with me just for a second here. Okay. .33 plus negative plus 1. Okay, my math was correct. It didn't look correct there for a minute, but it is negative 6.33. You can double check that math on your own there. All right, so that's going to now be our numerator in this piece over here. So if we're simplifying this kind of term, so this gamma 1 is going to be the sum from I equals 1 through 10 of the zi cube scores divided by n minus 1 will now become this negative 6.33 divided by 10 minus 1 is 9. And so if we divide by 9 here, we will get negative 0.703. Negative 0.703. And that is the mathematical piece here of being able to calculate skewness. And so if you have 0, if gamma 1, I just put it this way, if gamma 1 equals 0, then you have a symmetrical distribution, i.e. normal. If gamma 1 is positive, then you have what's called a positive shape distribution. And we're going to talk about the shapes of these in another videos, but you have a positive shape distribution, which means you have an increase in negative numbers. If gamma 1, that's an ugly gamma, let's try that again. If gamma 1 is negative value, then you have a, if I put these in circles, then you have a negative shaped distribution, which means you have an increase in positive numbers. So that's the basics of the math. So the essence is, the take-home story is, what do you want your gamma 1 to be? You want gamma 1 to be 0, which means that you are very close to 0. And then there are ways to test whether or not this is a significant departure from 0, the negative 0.703. We're not going to necessarily get into that, but in this particular case you would say that your shape of your distribution was slightly negatively shaped, and we'll provide an actual graphical picture to show you what that means. But this is the math behind it. So we'll need to do kurtosis as well, and then the shapes of these possible variations from normal. Thanks for watching the video on skewness.